before I start, so we received your submission for problem set 1, and the grading should be finished in 2 weeks, I think. And so I know that it can be challenging, the problem, but like the point is just like it's totally okay if you don't finish everything. And like my grading scheme is also not gonna be bad. Like I'm gonna be generous. Like the point is to give you this problem so that you can spend time absorb into this thing and think about it. And I think you say like once you get the like kind of get this moment when you see the solution, then it should be fun for you, I hope. Okay, and problem set 2 is already out, and yeah, you can look at it early just to finish it. Okay, so let's look at Dijkstra algorithm. So let's go through this pseudocode line by line and see what it does again. The problem is that you have the input is that you have a directed graph with positive length and some source S. And what you do in the beginning is you just initialize the finalized set to be empty and set this kind of tentative distance function D. It's just some array that you initialize. D of S, you initialize it to be 0, and everything else is infinite. And what you do is the following. You kind of just keep growing the finalized set until everything is finalized. On each step, what you do is you look at the node which is not finalized. The node that is have minimum tentative distance, which is not finalized. That's you. Add it into your set, and then relax all the edges that going out of the node U. By relaxing, it means that if you can, for any node V which is neighbor of U, if you can go through U to V, if this distance is less than like your estimate of the distance to V, you just kind of decrease this estimate to this thing. Okay. So that's the pseudocode. So let's see why this is correct. Okay. So the first thing that is kind of the key lemma is this. Suppose that, let's say that F is a finalized set, and what is going to happen is that I claim that throughout the algorithm, we will have this invariant. That is, for every node V that is finalized, we always going to have that the distance, our estimate is a real distance. So you're kind of done for every node that is finalized. Otherwise, for every node that is not finalized yet, we're gonna always have that the estimate is gonna be this thing, dfsv. So what do we mean by this? We just define this thing to be just this expression. So what is this? This is just the best, like the shortest length to go to V through only finalized node, and then plus one last edge. So it's like maybe I just draw. Like if this is your finalized set, this is your F. So what is gonna be what is V? What is dV? dV is just gonna be like the best shortest path, such that you only go through every node in F, right? And then one large edge here. That's the best. That's the df of SV. So even if there is like other paths that kind of go through many other things, if this is shorter, we don't count those. Okay. All right. So we will see soon why at every iteration we will have this. So we will see that. But suppose that is true. Okay? Suppose that is true. My key claim is that if you look at a node U that is not finalized and has like minimum estimate distance, like let's say like U is some node outside the set, but it has the smallest estimate. The claim is that the estimate of U at this point must be the real distance already. So you see, like, if the node U is outside the estimate, then we only, like, I only guarantee that the estimate of U is this thing, like this. So if U is outside the finalized set, we only guarantee that the estimate of U might not be the real distance yet, right? It's just this restricted kind of distance. But I claim that if U is the one with minimum estimate outside finalized set, this thing is already the real distance. Is the claim, the statement clear? Like at least the statement. Okay. All right. So now let's see why this is true. Okay. So let's prove this by contradiction. Okay. So if it is not true, then what do we have? We're gonna have that the estimate du is gonna be strictly larger than the distance. Right? And now, what's wrong with this? It means what? It means that this, suppose that there is like the shortest path here. Like, let's say that this is shortest path. Okay. And if the distance is less than du, where du is like the best way du is the best way to go to u through f and then plus 1h only. If the real distance is actually less than that, it means that the way to go to u must be that, okay, you must go out of f and don't use just 1h. After you go out of f, you don't just use 1h. You might use more than 1h, right? Because this thing is the one that you stay in f and then you just use 1h. But there is something else that is shorter. So this red one, the real distance here, must use more than 1h outside u. Okay. This thing must use more than 1h outside f, sorry. Yeah. Okay. So now what I want to do is just let v be just the first node outside set f in this shortest path. Which means what? This means that, so let's say that this is the shortest path p. Then the length of p is going to be this thing plus this thing. So it means that this length is going to be the claim 2v plus the distance from V to U. Okay. So if this is like, if I don't have F here, this is always true, right? V is a node inside the shortest path. So like both paths from S to V and V to U must be like the shortest path from S to V and from V to U. That's clear. But what I do here is that I claim that even if I add F here, that's fine. Why is that? Because this is a path such that by definition of, by my choice of V, this path is the one that keeps, like just stay in F all the time until the last edge. It go out of F. So this shortest path satisfies this criteria. So this SV and this SV with restriction to F is the same thing. Okay. So now now I want to say that, like what we want to say is that to get a contradiction, I want to say that this whole thing is at least F of SU. Why is that? Can you tell me why this is at least this? Yeah.
The definition of U is that it's the minimum that uses only one extra edge. So, so distance from S to V has to be at least distance from S to U.
Yeah. This thing is at least this thing just by the choice of U. Yeah. Choice of U is just the one such that this FSU is minimized. And what about this term?
By your assumption, it's positive.
Exactly. So we have that this is at least 0. And we need to use this at some point, right? Because otherwise, otherwise Dijkstra would work in non-negative with negative length. This is where we use the fact that the graph is positive. So this is at least positive. This is positive. And this is just by the choice of U. And so you see now, like this is a contradiction because like we have that this thing is strictly greater than this thing. So that's contradiction. Like the same thing is, like, it must be equal, but the left-hand side is strictly larger than the right-hand side, which is the same thing. Okay. So this is very important. Like it's basically the last, like the key lemma question about this. I can just go through it again if some part, like some step is not clear.
Would you please repeat it?
Yeah. So let me start again, right? So first, what I do is that I just assume by contradiction that this is not true. That's when I got this inequality. Okay. And what is du? Just by definition, like just from our assumption, du is this expression. Okay. And our plan is to show that this is strictly greater than the same thing. That's the plan. If we get this, then we're done. Okay. So now let's try to work with this thing. Like why this thing is at least this. So the first thing is that this is an important point. When you say that the real distance is actually strictly less than distance that go through F all the time and then just use one edge. If this happens, it means that there must be a shorter path that just goes through F and use more than one edge to U. Right? This is a path that I use more than one edge to U. And this is strictly better than like just go straight and one hop to U. So the red path is shorter than the green path. That's just from our assumption. And now I just define V. V is just the first guy that go out of F in this path. First, so let's say this is the path P. This is the path P. B is the first node in P, but not in F. Okay. So it must be there must be one node that is outside F. That's V. Okay. And so what is the length of P? It's just the length from S to V and then from V to U. Okay. But so it would mean that this is the distance from U to V is just the distance from S to V plus from V to U. But actually, the distance from S to V is the same thing as the distance from S to V restricted to F. Because this, by definition, is just a path that stay inside F and then just use one edge. And once we have this, we're done because this thing is at least this by the choice of U, and this part is at least positive. It's at least 0.
So is it true that vertices are added to F, like in the order of their distance from the source?
It's going to be like that, exactly. That's what's going to happen in Dijkstra. Okay. More question? Okay, so now what we're going to do is that we're going to use this key claim to say that throughout the whole process of Dijkstra, as Aditya said, the next node that we're going to add into F is just the next guy that is like the next closest guy to S, to the source. We're going to, like, the order of node that we add to F can be ordered exactly by the distance from the source, actually. Okay, so let's see. So when you want to prove that some algorithm is correct, right? One way to do that is to state this loop invariant and try to say that the loop invariant holds by induction, like say that, okay, in the first step, the loop, like this loop invariant is true. And if it stays true until the end, then you're correct. That's what we're going to do to prove by induction on time. Okay. So the loop invariant is exactly what we wrote in the last slide. Any finalized node have the real distance, and any one that is not finalized have the distance like restricted to F, like before. Okay. And okay, so what we do is that we just initialize this. Okay. And actually, maybe I I start where this is the finalized one is S. That should be better. Okay, so if this is the case, then you see in the beginning, the loop invariant is true. There is only one guy that is finalized and the real distance is correct. One sec. Maybe I just start with this. Yeah. Let's say that I initialize everything to be infinite for now. But let's say at least in the first iteration, the loop invariant, like once you finish the first iteration, the loop invariant is gonna be true, gonna hold. Why? Because in the first iteration, what will happen? U is gonna be S, right? And what you do is you add U into your set. And after that, what do you do in the third step? You really just say that for every neighbor of S, let's say this is V, just set dV to be, just set dV to be the length from S to V. That's what the third step does. And then you say like, now everyone that is not finalized gonna have exactly this property. We get that like our array D is assigned correctly. So you see like after the first iteration, the loop invariant, both of them is true. Both of them are true. So that's like the best case. Now let's try to do this proof by induction that the loop invariant, if it's true, like in the past always, then the next iteration is going to be true as again. Okay, so let's do that. Well, what do we do? Just by the key claim, right? We have that. We look at the node U. From the key claim, we have that this f of U is the real distance now. This is from the key claim, which means that when you look at the node U and add it to F, then the first invariant is now checked, right? You just need to make sure that you add someone into F. Anyone that you add into F must have the real distance, but we do. So the first invariant holds. Okay, so now you add something into F. Okay. We need to check how to make sure that the second invariant is true as well. That's where the last step try to do. That's exactly what it tried to do. Why is that? Well, you see, like what you do is that you have a set F. You just add some node U into the set, right? But anyone outside the set, we need to maintain that, like the D of V, like is the shortest way to go to V. If you keep going in, like if you go only through F and then use one edge. But U is the only new guy in the set. So what you need to do is just really look at how to go to U and use one edge. And if it's better, then you just update your estimate. So this is exactly what we do. And that's why the second invariant is true. So what do we get? We get that, okay, after each iteration, both invariant holds. And can you tell me why we are done now? Once we are finished, why this is correct? Because of what invariant? Anyone? Why are we done? Okay.
First invariant? What
Yeah.
if is everything, then the distance is, because the invariant is true then.
Exactly. We are done because of the first invariant. Yeah. Like anything that is finalized have the true distance, but we are done when everyone is finalized. That's when we get a real distance for everyone. So we can just return D because D is now is a real distance. And that's basically why Dijkstra is correct. Good. So question before I go to implementation. This is the correctness, the formal correctness of Dijkstra. Okay. So what we're going to do to implement Dijkstra is to use something called priority queue. Okay? And priority queue is just a data structure. Think of it as some black box. And this black box has like some different button that you can push and get something. It's just like some black box, some method or function that you, some class that with some method that you can choose what to do. So just to remind you what it is, priority queue maintains some set queue. And what you can do to it is to insert an element x with value k. So here it will just add x into the queue, and the value is going to be k. Value of x is k. Next thing it can do is, if you push the button delete min, it's just going to find a key, the key with minimum value, and delete that guy and return it to you. Next thing is decrease key. Given the key x and value k, you just check if, like, just make sure that the value of x is at most k. That's what it does. It's just some abstract data structure, and you can try to implement it in a different way. There are various ways to implement this. We're going to learn at least 4 ways how to implement this thing in this class. Okay, but let's say that suppose that there is some fast algorithm to implement each of these 3. Why we get a fast algorithm for Dijkstra? So it's actually quite simple. What we're going to do is just make the priority queue to contain every node which is not finalized. And so what we do in the beginning is just really just add every node into the queue. So that's in n insertion. And the value of each node is just this value d. Right. Now, what will happen is, you see, in each iteration of Dijkstra, what we do is really just, here we delete min. Just look at the node outside finalized set, just the node in the queue. Take the guy with the minimum value and delete it from your queue. That's delete min. So we're going to do delete min n times exactly. And then, what is this? This is again exactly the decrease key. For each edge that go out of you do the decrease key on the node P. So the number of operation of decrease key here, you're going to do it degree of u times. And we sum over all nodes u. So that's just kind of 2m. So we're gonna do decrease key to n times. Okay. So yeah, so now the goal is just how to implement all these three operations fast. So there are some ways to implement parity queue. Let's look at some trivial way. Suppose that you let's say that you know that there are just n elements ahead of time. What you can do in the beginning, when you insert, you just look at that index of array and put some number in it, takes constant time. When you decrease key, takes constant time to just change the value. But when you delete min, you just go through the whole array, scan through it. So that's n time. And if you just implement the parity queue like that, well, the total running time is going to be m plus n squared, right? Just because the total time is n times this thing, m times this thing, and n times this thing. So that's just at most, that's n squared time. It's quite good, but you can just do it better by not doing much really. So just instead of using array, just try to store all these key in a balanced binary search tree, right? And then balanced binary search tree can do a lot of things for you. Like you can insert, you can access on some node and change the key and so on, and delete the min guy. Everything you can do it in log n time. And just by that, you get the Dijkstra with m plus n times log n. Okay. So that's basically how you implement Dijkstra in m plus n times log n time. Later in class, we're going to see that you can actually improve it to m plus n log n. And we're going to do it using the best parity queue in theory that we know so far. It's called Fibonacci heap. Someone said that it's not good in practice. And I think it is not good in practice, but it's a good thing. It's a nice data structure to learn because it will guide you to this concept of amortized analysis. You will see how to use potential function and so on, some technique to analyze the data structure. Okay. Any question about Dijkstra? Okay. So let me wrap up about shortest path, static algorithm for shortest path that we have seen so far. We have seen all shortest path that use path doubling techniques in cube log n, and you can shave the log n using Floyd-Warshall. For Bellman-Ford, you can get mn time, and Dijkstra you get this time. Okay. There are many interesting improvements after this. Let me mention some. So one is that more than 20 years ago already, you can actually improve n to just square root n. And here it assumes that the length is integer. You can still handle negative length, but the length must be integer bounded by c. If that is the case, then you just pay log c here. And how about APSP? Well, if the graph is sparse, then the current best algorithm is actually by Seth Petty, another professor here. You see, if you do n Dijkstra, you can solve this using n Dijkstra, right? And you're gonna get n squared log n. So he can somehow change log n to log n. That's I don't know how, but yeah, that's cool. And as I mentioned, if you talk about dense graph, the best algorithm right now is by Brian Williams with this strange looking improvement factor. Last thing I want to mention is actually it turns out that just very recently, like some months ago, single source shortest path, even with negative edge. It turns out that now we know how to solve it in nonlinear time, m times log to the 8. This can be improved, but I don't know how much, but it's now nonlinear. So this is by Aaron Bernstein, Danuphol Nanongkai, which is my PhD advisor, and Kristin Wolf Nielsen in Denmark. So they get this result, and it's been in the news and get a Fox best paper. So Fox is like the best theory conference. Okay, so that's it about static algorithm. So now let's shift the gear and go to dynamic algorithm. Yeah. This one. Okay. Good. So this dynamic algorithm is actually my area of research. So I like it quite a lot. And as I said, right, like I mentioned this in the first class of this course. Like the graph nowadays are always really big, like a social network graph or internet graph and so on. And this graph keeps changing all the time. And what we really don't want to do is that when the graph just changes by 1 bit, we can just recompute everything from scratch. That's really wasteful. And what we want to do is, instead of recomputing everything, we want to do something better. Can we like just remove one edge and get something that is at least faster than doing everything from scratch? And that's what we're going to do today for shortest path algorithm. The algorithm is called Even-Shiloach tree. Is from 81, long time ago. It's simple, very simple, and it's actually the backbone of a bunch of other dynamic algorithms in the area. So we're gonna see this today, and so let's look at the problem. So what we have a graph, and let's say for now that for simplicity, the graph is undirected and also unweighted. Okay. So unweighted, I mean every edge have weight 1. And also m always is a number of edges, n is the number of vertices. We have a source S, but now the point is that now there is a sequence of edge deletion. So deletion only, okay? Like each edge deletion each deletion is revealed to you 1 by 1. Okay? And that happened until G is empty. But what we want to do is that at every time after each deletion, we want to maintain the single source distance from S to everyone. Okay. So if the problem is static and the graph is weighted, how would you solve this problem in linear time, in O of M time? If the graph have no edge deletion, how to solve this problem in OM time? Yeah.
You just do BFS.
Yeah, you can do breadth first search, right? Just look at the source, look at the neighbor of the source, and look at the neighbor of neighbor. This you can implement this whole thing in linear time. Okay, so that's easy, and which means that one trivial solution to solve this problem under edge deletion, you're gonna take at most m square time, because there are m edge deletion, and each deletion you can spend m time. So if you just do this, you get m square solution, but that can be as big as n to the fourth, right? If the graph is dense. Okay, so that's not so fast. And what we're gonna do today is that I'm gonna show you how to do it, like how to handle the whole sequence of deletion in total time, mn log n. So to handle the whole sequence of m edges, the total time is this. And when we have this kind of algorithm, that's when we say that the amortized update time is this total time over the number of operations. It's like the average time over all operation. So this amortized update time is n log n. Okay. So that's what it means by amortized update time. Is average over the sequence of operation. It's not average in the sense that the input is random and average running time is something. It's just the time per operation on average. Yeah. Okay. So, okay. Question about the word amortized update time is clear, right? Just total time over the number of operation, number of deletion. Okay. So this one, so at least you see this one, even in the worst case, you take n cubed, which is better than n to the fourth. All right, so let's see how to solve this problem. So what we're gonna do in the beginning is that initially, we just initialize the distance. Like we have the array for each node u, like the array that stores like the distance for each node u. So that's your estimate du, d tilde u. Just put it to just compute the real distance using BFS in OM time and assign that into du. So initially you are correct. And then whenever there is a edge deletion, what I'm gonna do is that I'm gonna call some key subroutine called update level of u and update level at v. Okay. So before I go through this pseudocode in details, let me show you the animation, how the algorithm works, and you're gonna understand how it works. Okay. So suppose that the source is a node A, and initially you just compute, do BFS and compute the level of each node. And you can also, by the way, you can always compute the tree, the shortest path tree itself as well. How? For each node, right? Just choose your neighbor with minimum level. Choose one of them. Like this guy, just choose this guy, this guy, this. Only one choice. Like the guy with minimum level is just here. And so if each node choose one parent, you're gonna get the shortest path tree. But you don't need to concern about the tree itself right now. Let's say that our goal is just to maintain the level, the distance. Okay, so in the beginning everything is correct, but what if you delete one edge, AB? First of all, what I'm gonna do is that I never gonna update level at the source. I won't call update level at the source, but I will call the update level at the endpoint of the deleted edge, which is now B. So what will happen at B is that it's gonna try to update its level to be the correct one. And what should be the correct level of B? Can you tell me from this picture? 2, yeah. Because the way to go, like the shortest path from A to B, like that is this one. So the level is 2. You cannot just take one hop anymore, but you can take 2. Now the way, so okay. So you can see that from this picture, B should be in level U. Okay? But actually there is like a generic rule on how to assign the correct level for B. So that rule is the following. Just look at all the neighbor of B, which is these 3 guys. Look at the minimum neighbor, like closest neighbor, which is now this guy. Look at the level and plus 1. Right? That's the way to assign the level, because you know that you can always go to any neighbor. You better go to the closest guy, but you take 1 hop to that guy. So you take, just look at the level of closest neighbor and then plus 1. That's why what you should assign is 2. So that's when you increase the level of B. Now when B increase the level, what will happen is that B will announce its level. That, okay, now it changed the level. So announce that to all the neighbor. Why do we want to announce that? Because you see, when B increase the level, there might be some neighbor of B that the level should increase. And in this case, who should increase the level?
E.
Yeah, exactly. So only E need to change the level, because this guy you still connect, each of these guys still have someone above you, but E doesn't have anyone above you, so E should increase the level. And the level of E is just look at the neighbor, look at the closest neighbor, closest to A, closest to the source is this 2, and then plus 1. So level of E is 3. And then when E increase the level, it always announce the level, right? And yeah, and now neighbor of E check if it should increase the level or not. And in this case, no one should increase the level. And that's when you stop. Okay. So what happened here is that when I delete an edge, look at the 2 endpoints, call update level at both endpoint. And now, whenever any node increase the level, look at the neighbor of those of you. Each of those neighbors should check whether you should increase the level. That's the algorithm. Let's try one more time. So you delete AC. Here, the level of C should change. What should it be? 3, yeah. So you just increase that, and then so you increase that to 3, and now the level. Each of the neighbor now should try to update the level if it need to. The only one that need to update the level is B. So do that, right? And B would announce that it updated the level, and no one need to do anything now. So that's when you stop. Okay. So, any question before I proceed? Okay, good. So now, yeah. So that's what exactly what we did. When we delete any node, when we delete any SUV, update the level at both endpoints. So what do we do when we call update level? We do anything only when this node is not a source. And what we need to do is we want to check whether this node need to increase the level. When do we need to increase the level? Only when the level of U is less than what it should be. Right? What it should be is, as I said before, look at your neighbor look at all of your neighbor, take the closest guy, closest to the source, and then +1. That's what your level should be. This is what it's supposed to be. If your level is less than that, then just make it correct. Otherwise, if this is not even true, you even do nothing. And the whole thing here would even take constant time. But if you need to increase the level. Okay. And now, whenever you increase your level by your level is more than n. What do you know about this? It must be the case that U is not even connected to the source anymore. Right? Because it's just too far. If you have any path at all to the source, it needs to have at most n hop. But if your level is now more than n, there is no way to go to the source. So you can just say that, okay, you know that you are disconnected. Just set it to be infinite and don't even look at it again. And that's when you're kind of done with U. But anyway, whenever you increase your level, you need to kind of alert to your neighbor that you have increased your level. So you just call update level at all neighbor of you. Question about the pseudocode? That's the whole pseudocode. Okay. So let me ask you for your understanding. So let's say that the graph is like this. Okay. What will happen to this guy when I delete SU? Can someone tell me what happened? like the evolution process, how would it happen? How does? Yeah.
So you'll call update level of S, and that won't work because it's the source.
Mm-hmm.
So then you'll call update level of U,
Mm-hmm.
and then use all of the neighbors have level 2.
Mm-hmm.
So U's level is going to be set to 3.
Okay. Now U is set to 3. Mm-hmm.
And then DU is going to be greater than N because there's only, wait. I guess it's not going to be greater than that, so I'm not
Not
sure.
yet. Yeah, it's not like greater than N yet.
So then you update level of V and W,
Mm-hmm.
and then their levels go to 4,
Right.
and then they get infinite,
Right.
and then U gets infinite.
Yeah.
Okay.
So exactly. So what's gonna happen is like it kind of keep trucking down to infinite. Like U and V, U and W, like VW is like this. When you update the level, it will go like to the next level here. This is level 4, this is level 3. Then you update the level at this guy. This guy gonna get to 5, level 5 now. And then you update the level at U, it keep going. And then once you reach N, then you say that you know that they are really disconnected from the source. Okay. So everything just keep going down until to level N, and then you kind of set it to infinite. Okay, good. All right. So one implementation details that I'm gonna do is that what I want from this implementation is, you see, when I check this one, I want to check it in constant time. That's what we want to do. It means that we want to maintain this number at all time. We want to have this number explicitly at all time. How do we have this number explicitly? Well, one way is just to put, like for each node U, we kind of have the priority queue for all of U's neighbor that contains this number, right? So I'll put all of this number in some binary tree. Yeah. That binary tree have size degree of U. Like there are just degree of U nodes, keys in this thing. So that, so let's say that we just put this in binary tree, or binary search tree, or binary heap. Then, whenever like some node decrease the level, some node V increase the level, means that it needs to announce to all of its neighbor to update. Like the use heap need to be updated once V's level increase. So, and this needs to be true for every neighbor, right, of V. So when we increase the level, you just kind of announce it to use to the neighbor and update the heap at everyone here. But to update a heap, you just take log n time, and there are just like how many neighbors are there? Just degree. So when you increase the level, you just need to spend degree times log n to update this number at every node. Make sense? Okay. Okay, now you see this algorithm looks correct. We're gonna prove the correctness soon, but the running time seems tricky to analyze because when you do something, it kind of propagate like there is like some butterfly effect. Like you do something, this guy need to update, and this guy might update, and then kind of keep calling each other like that. How do we analyze this kind of running time? So we're gonna do that soon. But before that, let's prove the correctness. Okay. So the first thing is that it's kind of straightforward. First, you see, I would just want to claim that if my estimate du is exactly what I want it to be, that is, look at the closest neighbor and like the neighbor with minimum distance and then +1. If this is the case for every node, then I claim that we are done. And this is kind of obvious. Like I would claim that if this estimate of S is 0 and everyone else is like what I want, like this, then the estimate at every node is just the distance. Well, this can be proved in like simple way by induction by the distance. And we'll not go into this. You can look at it. And once you have the true distance, you can maintain the tree as well, the shortest path tree as well. So you can kind of try to think about this at home. Why, like, convince yourself that this is good. And now, what I want to do instead is that I want to argue that, okay, the algorithm indeed maintain like this equality, the thing that we want on every node at all time. Okay. Like whenever the algorithm stop, like after some deletion, it keep doing a bunch of things. But whenever it stop, we know that this is true on every node. Okay. So what we're gonna do is just to prove by induction on time. Yeah. So this is usually how you prove the correctness of an algorithm. Just induction on time. So suppose that, let's look at each node u, right? And suppose that this equality holds until now. Okay. When can it be the case that this doesn't hold? Okay. This can happen like so. Okay. You can just need to see like when can this thing change. Okay. But this thing can change only one of the two cases happen. If some edge in this set, some edge that is neighboring u is deleted, then the set that we minimize over is changed. So this whole thing can change, right? That's the first case. And the second case is when the number inside this number itself change. That is, this level of v increase. So that's the only two scenarios that this number can change. But almost by how the algorithm is described, whenever either of these two things happen, just by how we describe the algorithm, we just call the update level and make sure that whenever this thing change, you set du to be that thing again. Okay. So that's why they are always the same. Because whenever you have a chance of changing that, you just make them equal again. Okay. So question? Okay, go. So now, so therefore, like this algorithm is correct. We get that everything is correct at all time. Now let's analyze the time. So there are 2 points to look at. The first point is that like the only non-trivial thing is the update level function, right? And you see, if when you call this function, and if you don't actually increase your level, what you do is just checking checking which two number and if it's true or not. So that just takes you constant time. So that's just constant time. But otherwise, this guy must increase. When this guy increase, like when you increase the level, that's when you need to announce to your neighbor and update the heap around you, and you spend degree for this is the number of neighbor, and for each of the neighbor you spend log n time. And another time that you need to do is just to the time to kind of call the update level. There are you call the update level on every neighbor of you. Okay. But the point is, whenever you increase the level, you spend this much time. So let's just analyze the time that you spend on update level u, but you don't count the recursion. Okay? The time the time to call this, excluding the recursion, is just degree times log n. And now, for every node, so this is now the key point. Okay, you have that for every node u. Okay, a lot of complicated things happen, but no matter what happened, you have that it never increased by more than n times. Okay, because otherwise, you set it to be infinite and you never increase it again. So now that's the point. It just means what? It means that the total update time that you just ever spend on update level u, when you might count this many times, right? But the total time that you ever spend on it outside the recursion is just n times this thing. And that's why the worst case update time, you just sum up over all nodes. And that is n log n. So you see, we don't even try to analyze the time per operation. One operation might change a bunch of things in a complicated way. But you know that no matter what, this thing never increased by more than n times. And this is the only case where you need to spend some non-trivial time on the update level. That's when you spend degree time. So you spend degree time, but that happens only n times per node. Summing over all nodes, you get m log n. Okay. Question? Good. So yeah, and this is kind of the time for all mh deletion. That's why we said that the amortized deletion time is just the whole total time over m. So that's n log n. So now let me ask you some exercise to think about. So can you try to tell me what should be the algorithm when instead of you have only h deletion, you have only h insertion, and the initial graph is empty? how the algorithm should be. Okay, so anyone on the back, you want to try to just some random idea would be fine. You want to? Okay, so you two have some idea, so maybe start with you or start with you. Yeah.
Okay. I feel like it would be the same time complexity at least, because basically like I think the key step is where you like set it to infinity, and in this case, it's the distance is always going to be decreasing, and so at the start the distances of everything except for the source is going to be infinite.
Mm-hmm.
And then the only time it decreases from infinity to like an actual like number is going to be when it gets connected, where there's like some path from there to the source. And then after that, the least it can go to is 1.
Yeah.
And so when it's connected, the most it can be is n. So the total distance from any node to the thing is always going to be either infinite or any number from like 1 to n.
Mm-hmm.
And so that's also bounded by n. So like it would be the same time complexity, I think.
Very good. Yeah, very good. That's exactly how it goes. So the point is that, so you see, whenever you are like this invariant where like when you are not you, and when there is an edge insertion or some node. So first of all, when you insert only, the distance only decrease. It keep getting closer and closer to the source. Right? And as long as you just do the same thing, that is, whenever you insert some node, or your neighbor decrease the distance, you just try to update your distance, just like before. If you keep doing this on every node gonna get the correct distance. Just like here, whenever like some edge is deleted or some of the neighbor increase the level, you try to up the distance. Here it's just the same. Whenever an edge is inserted or some of your neighbor change the distance, just update your own level. If you keep doing that, it's going to be safe. Like it's going to be correct. And the running time is also going to be like before, because now, no matter what, each node just keep decreasing its level, but that can happen only n times. So the total time is just again this thing. Good. So now, okay. What if I promise that the distance is always at most d? Then now you see, like we can just improve the total update time to be at most md immediately. Because now instead of saying that each node can go from from some number to n. Now it's like just go from some number to at most d. And just replace this thing from n to d. And that's when you're done. So if it's h have weight now, at most w, now you can say that the total running time is at most mnw. Because the number of level, instead of maximum n, now it's maximum nw. Okay? So, and so now, last thing is, if there are both insertion and deletion, actually the algorithm is still correct as again, right? Just like before, if you are u, and whenever like there is an endpoint of like u is an endpoint of update, whether it's deletion or insertion, or the neighbor of u change your level, and then you just call update level, you're gonna get the correct answer at the end. But can someone tell me, also the algorithm is correct, why would the update time go badly? Like why this algorithm doesn't look good at all when there are both insertion and deletion?
The same pattern might just repeat, right? You insert the edge, you delete the edge, you insert the edge, you delete the edge.
Yeah. And like, can you tell me a bit more why that's keep you bad running time? So yeah, the thing is like, yeah, do you want to say something?
I think like you can't make like the bound assumptions anymore, because if you can insert, then you can make like a really, really long path to some node, and you can't say like once its distance is above some threshold, like oh it's disconnected. It might actually still be connected. It's just like a really long path.
So that's not quite the point, I think. The key point is this. If there is only deletion or insertion, the distance on every node is monotone. It goes only on one direction. So it means that no matter what, it changes, but the total number of times that it changes the distance is at most n. Every node changes the distance at most n time, if the distance is monotone. But if there are both insertion and deletion, well, now each node, it can be the case that for one, like just maybe imagine this. There is a one big click and then the source. And then I keep deleting and inserting this edge. In the beginning, when there is an edge, everyone have distance like 1 or 2. When I delete, now the whole distance increase from 1 to n, to infinite. Insert again the whole thing in, like one update might change the distance by n. And so now for one update, like the total distance that you change is n. It's not like for the whole sequence of update, you can say that each node change the distance at most n time. Now it's just one update, you can change the distance by n. So that's like it can go up and down for the whole sequence, and that's really bad. So let me finish up in 1 minute. So just to tell you some state of the art. So we get that we get mn log n with some a bit more like it's actually still simple. You can actually shave this log n. You can try to think about that. And it turns out that natural question: can you improve mn? It looks not so fast, right? It's still kind of cubic in the worst case. Turns out that no. Otherwise, you would contradict some conjecture. that I and my co-author made some times ago. And that conjecture is quite believable. So you can have a look at the paper, or I might talk a bit about this at like last part of the class. Turns out that, okay, the next best thing that you can hope for is, what if I allow you some approximate distance, like 1 plus epsilon approximation, really close to the base. Turns out that once you allow some epsilon approximation, you can get something really close to linear total update time. So that's great. And once you so there was an algorithm that is randomized, and we make it deterministic. And then there was once you get this, you can use it into to get some more application like fast max flow and linear programming and so on. So yeah, lots of things still going on. And but anyway, the next class we're gonna look into amortized analysis in more details and techniques how to do that. Okay, see you.